Hello, we're here to evaluate some problems. So again, this is 6.7. We're getting a little bit into 6.8, which is evaluating integrals. Again, these are all indefinite because there is no bound. So I want you to take a couple minutes here, right? Not just one, multiple minutes here, and try to solve these out. So stop the video when you're done, come back to check your answers. Okay, so the first one with A, this is a simple undoing the power rule. So because it's x to the fifth, the integral will be x to the sixth. Because I have a coefficient of 1 in my original integral, this becomes a 1/6. And of course, we can't forget the plus c. For the second one, we're getting a derivative of, or we have an integral of 5 secant squared x. Sometimes you'll also see this written as 5 times the integral of secant squared x. And we know what has a derivative of secant squared, that's going to be tangent. So this is just equal to 5 tangent x plus c. C is another example of power rule, except it's a little bit harder to deal with just because we have this fractional power. So when we take the antiderivative here, that's going to get us x to the 3/2. We're adding 1 to 1/2. To deal with the coefficient that we should get from 3/2, which would be 3/2, we're now going to make it a 2/3. So when we take the derivative of this, we'll just get an x to the 1/2. For D, again, we can consider this a power rule, which isn't too bad, right? This just says, okay, well, that would become x to the negative first, and then 8. However, there's no negative in front, which we would have if we took the derivative of this function. So we slap a negative on there as well. Again, plus c. You'll probably never see this as a final answer. Most of the time, they'll actually show it as negative 8 over x plus c. E. So if we try to do the power rule with E, that would essentially work like this, right? This is the integral dx, and so if you tried to add 1 to this, you get 8x to the 0, and so you're like, wait, is it a constant? That doesn't make sense. And you're correct, it doesn't make sense. Instead, we're going to deal with it as follows. This is essentially just equal to the 8 times the integral of 1 over x dx, which means this is equal to 8 natural log of the absolute value of x plus c. Again, all of these plus c. F, I don't even know why it's sneaking over here, right? This is literally just x squared plus c. G has a little bit of work in the fact that we actually should probably take that power and multiply it out. A lot of times you'll see something like G, we're going to get to what's called U substitution. But right here, this is easier for me to just go 1 over 8x cubed dx. So here we're going to use the power rule again. That makes it 1 over 8 times x to the second, right? We're adding 1. Remember thinking about this as 1 over 8 times x to the negative third. So what that means is we should have a negative 2 when we do the power rule. So this becomes actually a negative 1/2. And so now this 1/8 becomes a 1/16. So again, think about, okay, well, if we brought this up a power, that gives us x to the negative second. And so 1/8 times negative 1/2 gives us negative 1/16. And again, plus c, always plus c. You don't have bounds, throw a c in there. All right, next set. Hopefully that wasn't the worst. Let's try the next set, see how we're at. Ooh, H looks fun, and these all look fun. Take a second and pause the video, see how you feel about these. Okay, so H just has a bunch of little functions in it. If we wanted to, we could break this down into the integral of 4x cubed dx plus the integral of negative 3 to the x dx plus, I think you understand what I'm going with here, right? We could just do the integral of each single one of these as their own specific function. This works because we're dealing with addition. This does not work if it's division, right? But because addition or subtraction, we are able to just integrate each piece at a time. So the first thing we're going to do here is say, okay, well, what's the antiderivative of 4x cubed? That would just be x to the 4th And the 4 divided by 4 gives us a coefficient of 1. This minus 3 to the x would have a minus 3 to the x, but we know if we're multiplying by, if we were doing the derivative of 3 to x, we'd have a natural log of 3 out front. We don't have that, so we do 1 over the natural log of 3. Then what has the derivative of sine? That would be negative cosine. And then lastly, what has the derivative of e to the x? That's e to the x. The negative 5 doesn't change that. We leave it as is. And then plus c as a final answer. All right, for I, notice how this divisor is a single term. That's really helpful for us. If this were to have like x to the 4th plus x squared, this problem becomes a whole lot more difficult to deal with. But here we can just divide each one of these out. So let's simplify this down to x cubed minus 5 over x plus 2 over x cubed dx. This is much easier for us to integrate. We would just get a 1/4 x to the 4th, or x to the 4th over 4. This becomes a minus 5 natural log of the absolute value. Make sure you guys remember that absolute value here. This becomes a minus 1 over x squared and plus c. All right, J. J is an example where if possible we could do u sub, and again we'll talk about where we get u sub from, but it's a lot more work than just actually multiplying that out. I rewrite this as x squared plus 3x cubed dx. Make sure you put parentheses around that whole integral, and then we're just integrating each term. So the antiderivative of x squared is x cubed over 3. The antiderivative of 3x to the 3rd would be 3 over 4 x to the 4th. And then finally, plus c. Okay, hopefully those weren't the worst, because these two are harder. So again, stop the video one last time and see what we get with these two. Okay, for this first one, we have a problem because it's divided by cosine squared. And so instead, why don't we rewrite this as the integral of sine of x over cosine of x times 1 over cosine of x dx. We can then realize that this is really the integral of tangent of x, secant of x. Oh, and that's not too bad to deal with, right? The derivative, what has the derivative of tangent secant? That's right, it's just secant of x. And then plus c. And then this is actually a trig identity. Oh my goodness, we need to know our trig identities. This is cosecant squared x dx. And so this will just equal negative cotangent squared x. Again, slap a plus c on there and you're done. I hope these problems were helpful. Again, these were all indefinite. If we just change these to definite, then the last step we would have is, let's say, plug in AB, right? So if this is in a definite integral, then the last thing I'd have to do is actually just plug AB in, and it would look like negative cotangent squared of B minus negative cotangent squared of A. So that's kind of just an extra little step that we have to deal with. Those are more application-based problems you're going to see a lot, but here we're just doing a regular indefinite integral. So we're just finding an antiderivative and slap that c on at the end. All right, as always, if you have any questions, please feel free to reach out and ask. Otherwise, have a great day.